most of the audience I see is members of the participants of the school. So maybe my introduction is not going to be as detailed as I planned it to be. Apparently, most of the Boulder public is not that interested in popularity. So I mean, I don't know what that says about Boulder. Maybe they're all more interested in working out than popularity. But anyway, so as you guys know, I'm a professor here in the physics department, and it gives me a great pleasure to host this event, a public lecture, to welcome you here and introduce our tonight's speaker. But before I do that, just in case there are some members of the public here, I want to give you some background on this event. This series of public lectures, one tonight and one a week from tonight, same place, same time, is part of the Boulder Summer School for Condensed Matter and Materials Physics that we hold here in the physics department every July. And this year is our 10th anniversary, so we're very happy about that. So this is a school that is held every year, and it picks out 60 to 70 best and brightest international students, best and brightest, here we are, to come to Boulder to have fun and to learn all kinds of esoteric physics from best and brightest lecturers and professors from around the world, and on a variety of topics. So this year's topic is on non-collision physics, dear to the heart of anybody who's alive. And so, and the school is supported by National Science Foundation, which is really, taxpayer dollars at work. And so every year we put out these kind of public, as part of the school, we have these kind of public lectures, 1 or 2 lectures per school. So tonight's speaker is Professor Sid Redner from Boston University. Sid is a distinguished expert on the subject and has contributed to it over many years. He's also well known for his ability to lucidly expose the audience to the subject that's actually quite sophisticated, quite complicated, but he's always able to take this very sophisticated subject and present it in an extremely easy and sort of palatable way, as he will show tonight. So Sid, to give you some background on Sid, he was an undergraduate at Berkeley, got his PhD at MIT, and then after a short postdoc in Toronto, moved to Boston University, where he's been for the last 31 years. So tonight's talk is on the statistical mechanics of popularity, and it kind of demonstrates that, in right creative hands, methods that we utilize in physics find many applications well outside of the simple, most usual physical applications, such as optimizing your popularity. So please join me in welcoming Sid.
Thank you very much. I'll just turn this on. Turn it on. So it's a great pleasure to be here. This is my second visit to Boulder, and I really enjoyed it. I enjoy going to the gym at 6 o'clock while I'm Eastern time. So statistical physics and popularity. So this talk is really geared to the non-school members here, and I hope that you'll feel free to ask questions if anything is unclear. So what do I mean by popularity? And this is what I mean by popularity, is People magazine. I admit that I read People magazine when I go to the dentist and the doctor. And I don't know if any of you are willing to admit it, but anyway, it's a great source of information. I mean, here's Brangelina, here's Jen, here's J-Lo. I wouldn't know that without having People magazine. And so the question I want to address here is, how do we characterize popularity? Why is Brangelina on the cover of People and not me? How do we characterize popularity? How do we quantify it? So that's basically what I'm going to be discussing. So let me show you a couple of examples from real pop culture of ways that one can characterize popularity. And one thing about what I'm going to show you tonight is that because of the advent of the World Wide Web, anybody can be a popularity theorist because there's all kinds of lists. So here's the hottest dates. And so depending on your taste, on the left column or the right column, I have to admit, I don't know half of the people on this list, but one can go to this website and look at who's hot, who's not, and this changes like from week to week. And so here's the top 5 hottest days. Another example of this, and this comes from the U.S. Census Bureau. If you look in the Census Bureau, they have all kinds of interesting statistical information on which one can actually make physical theories. And so here's one, the top 10 baby names. And so in the year 2008, here they are, the top 10 baby names. Females, here they are. And just as a matter of some amusement, you'll see that there's William and Elizabeth, which are bold-faced, and everything else is not. And the reason they're bold-faced, if you go to 1908, 100 years ago, only William and Elizabeth were in the top 10 names. And you see names that sound maybe really antiquated, and you get a sense, comparing between 1908 and 2008, just how different names have changed. So what is it about names that became popular? What is it about naming that some name is popular in 1908 becomes unpopular in 2008? And I would say that this is really not a very well understood problem. It's just something fun to think about. Why do names become hot for a while? Why do they disappear? Here's another one that probably all of us have some feeling for, about the top grossing movies. And here I'm going to do it inflation adjusted, so that we don't unfairly penalize the old great movies. And so if you look at the top, I guess it's 25 I have here, Gone with the Wind. How many people have seen Gone with the Wind? How many people haven't seen Gone with the Wind? Oh, anyways, so it's pretty predictable, the top 25 movies. Here's another one that probably we all have a feeling for. And who's number 1 on this list?
Can we go back to this? I want to jot it down for my...
Which ones are on the stage? Okay. Anyways, richest people. Who's number 1 on this list? Okay, so you all know that. And if you go down the list, it's amazing, first of all, he was 57 billion just a year and a half ago. I think he gave a lot of it away, but it's not because he lost in the stock market. If you go all the way down to number 27, 28, I just want to call your attention to these 2 names. Maybe some of you recognize it, Sergey Brin and Larry Page, because these are the guys who created Google. And I'll come back to Google later on in this talk. The last example I want to show from this popular culture is one that's going to now become a little bit more quantitative, and I'll begin to show you how statistical physics starts playing some role. And so this is word popularity. What is the frequency of different words that appear in the printed English language? So there's a project called the Gutenberg Project, which has put a large number of books, categorized every single word in these books. And so you can count what is the most popular word in the English language, what is the most second popular word in the English language in this large corpus of literature. And so if you look for the top 25 words, it's pretty obvious. It's not all the words that we're all familiar with. And so they appear in the top 25. But this word list goes down to word number 100,000. And so if you go further down the list, so if we go between 1 and 25, everybody recognizes that these are words that are appearing all the time. From 101 to 125, they're also pretty common. But then you go further down the road, from 1,000 to 1,025, well, probably all of us know what all these words mean. But once you go down to 10,000 and 10,025, well, probably almost all of us know what all these words mean, but there's some that are a little bit weird. I thought there was Miranda. There it is, Miranda. And then if you go to 20,000 to 20,025, well, irrefragable, meretricious, phantasmagoria. So if you need help with the New York Times crossword puzzle, this is the place to go. So anyway, one sees that as you go from very popular to less popular, there's, these you barely use in everyday language. These are very common. There's some other things which are a little weird about this that I don't think have ever been thought about. You see that for the most popular words, the words are always very short. And here they're getting longer. If you go into 100,000, they're even longer still. And in fact, most of the words I don't even know what they mean. And so it's interesting to try and quantify what's going on with this word frequency. And one attempt to do this was already done in before I do that, let me just come back to,
Where does physics show up on this thing?
Where does physics show up on this thing? Very good question. And in fact, I'm sorry that this is scrolling through so slowly, but that's in fact my exact next slide. So there's the title again. And so you might ask, which is you just asked the question, what does popularity have to do with statistical physics? So let me give you now a short answer to it. The first part is the word statistical. So I want to define the title of this talk now because you all have a sense of popularity is, but maybe some of you don't know what statistical is or what physics is. So the statistical part is that we want to take popularity data, the hottest dates, the most popular words, the richest people, and look for quantitative patterns in the data. Not just like a list that you can just put up and put up on a website, but something that you can say something quantitative and crisp about. And then the part about physics, and this is what physicists really think they like to be able to do, is that to construct fundamental principles that can explain the data. So there's two parts here. Statistical and physics is, first of all, determining the quantitative patterns in statistical popularity data, and then constructing some fundamental principles or fundamental theories to explain the data. And in some sense, statistical physics is a field that's very different than most other fields of physics because if you hear about, like, say, cosmology or general relativity or quantum mechanics or high-energy physics, there's a real clear holy grail of what one is looking for. But in statistical physics, it's not necessarily one problem that everybody's looking for. But I hope I give you a sense from the list you see here that statistical physics is everywhere around you. You look at People magazine, you look at the dictionary, you'll see all kinds of manifestations of statistical regularities that, if you put it in the right framework, can inform new physical principles. So let's now look at the patterns of word popularity. And so I want to point out a very beautiful work by George Ziff in 1949. He wrote this beautiful book, Human Behavior and the Principle of Least Effort. And so the point is that he was trying to develop a theory for what was the word frequency in language. And his idea was that language is developed to be as efficient as possible. And you want to use the least amount of effort to communicate the most amount of information. And so he came up with a theory that if you plot the popularity of a word as a function of its rank, so the most popular word is the, and so it has a very high frequency. The next most popular word, I guess, was of or a or something like that. It has a lower frequency. If you plot word popularity as a function of rank, it lies on a well-defined curve. Now, there's another thing about this slide that I want to show you, which is that this is an absolutely terrible way to present data.
Sorry, what is a rank?
Pardon me?
What's a rank?
Rank. So, the is the highest rank word. Of is the second rank word. So, rank 1 is the. Rank 2 is of. Rank 3 is at, and so on down the road. So, I'm plotting the frequency of the word the, and it's rank 1, and then so on and so on.
But rank is not popularity?
Rank is popular, yes.
You plot in 1 over x.
No, I'm sorry.
Not the rank as the length?
No. This is correct. What the word popularity means is how many times the word appeared.
Oh.
So I have like a corpus of like 10,000 books, and here this is word popularity divided by 100,000. So this word, the, appeared essentially 550 million times in these, several thousand books. And then the word of appears like 475 million times and so on down the road. So the, which is here, is rank 1, add, rank 2 is here, and so on. When I get down to rank, say, 1,000, whatever word that was, it appears much less often. It almost looks like 0 on this plot. Anyways, the other thing that I wanted to point out here is that this is an absolutely terrible way to plot the data. And why is it terrible? From a purely artistic perspective, all the data is scrunched at the y-axis and the x-axis. You can't really tell anything from this. And so this is another interesting aspect about looking at the data with the right eyes, because when you look at it with the right eyes, patterns come up very easily that you won't discern unless you always are willing to twist around a little bit and look a little bit backwards at the data. And so what physicists would plot, let's say here, this is a linear plot. If I go from 0 to 200, the distance from 0 to 200 is the same from 200 to 400, which is the same as 400 to 600. So everything's being plotted on a linear scale. It turns out that for this kind of data, the right scale is what's called a double logarithmic plot. So let me show you the same data on this double logarithmic plot. where instead of plotting on a linear scale rank and linear scale popularity, I'm plotting logarithmically. So what this means here is that rank 10 to the 0 is the number 1. So rank 1 is sitting here. This distance is a factor 10. The same distance is another factor 10. The same distance is another factor 10. So you have going from 1 to 10 to 100 to 1,000, and the distance between 1 and 10 is the same as 10 to 100, which is the same as 10 to 1,000, and similarly on the y-axis. And when you plot it on this double logarithmic plot, that data which was scrunched down into the very left corner and you couldn't really see what was going on, is now bashing over the head with the fact that it looks like for the tail of the distribution out here at very low rank and relatively low popularity, it looks almost straight. And in fact, if you try and fit a straight line to it, it's not a bad fit to the data at all. And in fact, this fits that the popularity of a word, how often it appears, as a function of its rank, popularity proportional to 1 over the rank is what the red line is. And in fact, that is precisely what is in the theory of Mr. Zipf in 1949. He predicted that the relative frequency of a word, how often it would appear, would be proportional to 1 over its rank. So this theory that came up in 1949 has only been tested in a proper way in the past decade with these large word projects, which have been categorized large bodies of literature and have been able to find this in a very nice way. Now, it turns out I've actually cheated a little bit here because if you actually fit the data properly, like using some software, you find that the best fit to the data is actually not 1 over rank or 1 over rank to the 1.07. But it's not a bad fit at all to the data. And given how simple the principles are behind Zipf's underlying theory, this is really what I would consider a real success, intellectual success, to come up with a theory that could only be verified 60 years down the road. Now, what I want to turn my attention to now is something a little bit more near and dear to the hearts of physicists, because you might ask, so why should physicists care about anything to do with popularity? And part of the reason is what do we do as physicists? If you are, at a time of tough budgets like we have now, maybe here in the state of Colorado, you might hear in the newspapers from the state legislature, oh, the professors are so lazy at the University of Colorado, they only teach 3 hours a week, and, what the heck are they doing? They're just teaching 3 hours a week. It's a cushy job. Let's, triple their teaching load or something like that. But any physicist who's worth their salt will say, inside of my soul, what I really love doing is physics research. And what physics research involves is coming up with a problem, writing up a physics publication that you then publish in some journal. And the major journal of physics in the United States is something called the Physical Review. So this has been a physics journal which has been in existence since 1893. And essentially every working physicist has published papers in this journal. And what I want to show you now is some interesting statistical information about citations from the Physical Review. Because what we as physicists also want to have, not just that we write papers and we put them in some journal and they're forgotten forever, we want other people to care about what we do. Just as like J-Lo cares about how many people come and see her movies, we care about how many people might actually read our papers. And the way that we quantify how many papers are actually, how popular our papers are by citations. So if I write a paper and it's a really good piece of work, then other people come after me and say, oh, let's cite this paper by myself, and in so doing, I become better known. And so what all physicists care about, and all tenure committees care about, and all university administrators care about, is how often are your papers cited. So I want to now show citation data from the Physical Review from the period 1893, from the creation of the journal, to 2003. And in this 110-year period or so, there have been a total of 350,000 papers written inside of the Physical Review. And if you count up every single reference in every single paper, there's a total of 3 million citations. So if you just do the algebra, divide 3 million by 350,000, you'll find that the average paper in Physical Review is cited 8.8 times. So I write a typical paper, and 8.8 other physicists are going to say, that sounds a little interesting, and cite my paper. And the other thing about this 8.8 is, here's another interesting number, citation age of 6.2. Now, what I mean by citation age is that if I write a paper in the year 1990 and someone cites me in the year 2000, that's a citation which is 10 years after my paper. And so that would be a citation age of 10. And if you average over all papers, you find that the average paper is cited about a period of 6 years before it disappears off the face of the earth. So this gives you a sense of how much attention we physicists get. We are typically cited 9 times, and we are cited over a period of 6 years, and their papers are forgotten. Now, one other thing about this data is that the Physical Review is the largest physics journal in the world, but it's not everything. And this data set is only looking at citations from Physical Review papers to other Physical Review papers. So we're looking at what might be called internal citations only. And so this undercounts the total number of citations by some fudge factor that I don't know precisely, but the best estimates by looking at a subset of all papers is somewhere in the vicinity of 3 or 5. So for this number of citations, even though it's 9 for internal to Physical Review, the right number is somewhere in the vicinity of 35. It still gives you a sense of what is a typical citation of a paper. Now, in addition to looking at the averages, again, in statistical physics, we're interested not in just the average, but in the distribution. And one way to characterize the distribution are some of the outliers in the distribution. And so, for example, we can look at papers with more than 1,000 citations. And it turns out that until July 2003, there's been a total of only 11 papers with more than 1,000 citations. So you have to, out of all 300,000 papers, 11 with more than 10,000 citations. So these are really quite rare, and they're all exceptional papers. And if you go down in your criteria and say, let me look at all papers with 500 citations or more, one finds 79 papers. And once you go down the list gradually with making the bar a little bit lower and seeing how many more papers you find, and once you get to 100 citations, there's 2,000 papers. 50 citations, there's 8,000 papers. So already at the level of 50 citations, which is much bigger than the average here, there's relatively few papers. There's only like 2.5% of all papers that get cited more than 50 times. The dark underbelly of this data, however, is the other side, which is that if you look at less than 10 citations, which is basically the average or less, 245,000 papers. So more than 70% of all papers are cited the average or less. And if you are really sadistic, you can look at the papers that are down at 1 citation, 84,000 papers. And what's truly an achievement, and for those of you who are non-physicists, I'll explain why it's an achievement. There are 22,000 papers with no citations at all. And for the non-physicists in the audience, when you write a paper, it's almost impossible not to cite yourself because you're working on your own research program, which is based on things you did in the past. So if you don't cite yourself, that's really a damning characteristic. So let me now turn to...
But excuse me, that 0 is only inside the Physical Review. You can't multiply that by 5.
That's right. So, yeah, it's possible that if we do this multiplication by 5, there will be fewer non-cited papers. But, yeah, your observation is certainly correct. Anyways, I want to now turn to looking at another aspect of the citation, which is coming a little bit back more to statistical physics, which asks the question, what is the chance that you'll get cited? So I want to show you the result of a numerical experiment I did, where I calculate the chance of actually getting cited. So I take all the Physical Review citation data, and I look at all papers published between 1893 and 1999. So there's, whatever it is, it's 300,000 papers. And for each paper, I count the number of citations to each paper. So there's a variable here, n, which is the number of citations to each paper. So this is a measure of the current popularity of a paper. And now I imagine I'm living in the year 2000, and in the year 2000 I count the number of new citations to all these previous papers. So the number of new citations is capital N, which will depend on little n, the number of citations the paper already has. So what I'm measuring here is the increase in popularity as a function of the current popularity. I want to decide if a paper is well cited now, will it be more likely to be cited in the future? Is there some correlation between little n, your current popularity, and big N, which is your increase in popularity. And so here's the result of this experiment. So here is the data itself. So I'm plotting on the y-axis the number of new citations. This is this capital N as a function of little n, the number of citations a paper already has. And you see that the data is not terribly smooth, and in fact I've already smoothed it a little bit, so there's a little cheat here to the data, which is if you have very chunky data, you smooth it a little bit so you can see some systematic trend. But anyways, the point here is that if you just draw a line through the data, it's not a bad fit. And this strong correlation, especially, the other thing about this fit here is that most papers, we saw that there was 2.5% papers outside of 200. So this data is really out in this extreme tail. And here, very close to the origin, this is where almost all the papers lie, and the fit there is extremely good. So the conclusion that comes from this little measurement is that the probability or the rate at which the popularity increases is proportional to your current popularity. If you're well-cited now, you'll be well-cited in the future, just by virtue of being well-cited now. Notice that here there's no measure of quality or anything like that. All that matters is how well-cited you happen to be now. So the conclusion from this is that the citation rate, the number of new citations in any given year, is proportional to the number of citations that you have now. It doesn't matter about quality, it doesn't matter who you are, it doesn't matter what university you work at. Just how many citations you have now, that will tell you how many new citations that you get. So in fact, this has a biblical origin known as the Matthew effect. So for to all those who have, more will be given, and they will have an abundance. So those have get more. But for those who have nothing, even what they have will be taken away. And so I'm not much of a New Testament scholar, but it's there in the New Testament. And this idea of the Matthew effect is popularized by sociologist R.K. Murphy, who in fact had a son, R.C. Murphy, who won a Nobel Prize in economics. But this guy was perhaps the best sociologist of the past century. And so what he called the Matthew effect, and we know it in current physics literature as a notion of the rich get richer, but it's also something we've all seen and we all probably complain about. You know, someone is advantaged, they have the nicest house, and so they have the nicest furniture, they have the nicest house, they get the nicest wife or something. So the rich get richer. And so what we see here is that the data is very much in accord with the rich get richer. Now there's another important lesson that comes out from this, which is that what it really means is that there is this rich get richer effect in the context of citations. Because when I write a paper, I don't look at the entire physical review data set and say, well, this paper was cited 1,000 times, this paper was cited 10 times, so 100 times more likely I'm going to flip a coin and cite this one paper over here. I don't do anything like that. I say, well, I'm working in statistical physics, I care about statistical physics, so I'm going to cite other papers that are coming before me in statistical physics. I don't care about hydrogen physics, I don't care about astrophysics. So what determines how I decide my citations is an individualistic behavior depending on my own interest. And since my interests are very different than anybody else's interests in this audience, what I would say is that there is individual behaviors and they're very complex in their origins. We have different motivations for why we're going to cite it. So the crucial point here is we have a very simple result here. But it's coming, the origin microscopically at the level of an individual is complex. And the point is that starting with the complex behavior of each individual, what emerges, so this is a buzzword that appears in statistical physics, the notion of emergence. That you start with complex individuals, and then at the collective level, this simple behavior, citation rate proportional to the number of citations, emerges from the complexity of all the individuals. You take many individuals, the entire set of all physicists working around the world that publish in physical review, and each one is complicated, and yet what emerges is a simple property, citation rate proportional to the number of citations. So I think this is actually a very important lesson that we get from this data, is that this notion of emergence. And so in this summer school that we're having here, this notion of emergence is like underlying so many of the talks that we have, where we are studying simple models that have beautiful emergent properties. And so here the simple emergent property is that the rate that you're being cited now is proportional to the number of citations you have and nothing else. So I want to now turn a little bit away from quantitative and again more in the framework of entertainment. Tell you a little bit more about kind of the gossipy end of citation histories by presenting some outstanding examples from physical review of citation histories of very special classes of papers. So I'm going to focus on two types of publications. One, the great discovery papers in physics. And so what do I mean by a great discovery? Well, a great discovery should have a lot of citations. So in this example I'm going to present, I'm going to look when the number of citations is larger than 300. So that's about 2% of all papers. But moreover, in order for it to be a great discovery, what does it mean to be a great discovery? You discover something great, and people say, what you've done is great, they cite you right away, and then eventually, well, people have forgotten about you because it's obvious you did something great, and then it becomes part of the canonical information, and there's no reason to cite you anymore because, for example, Newton, nobody cites him anymore because we all know that the world goes by Newton's laws, and so there's no need to cite his Pixie mathematical. So what I'm going to look here, what I'm going to present to you then is a citation history of discovery papers which have more than 300 citations, in which the citation age is early in the lifetime of the paper. So what I mean, for example, is that if a paper was published 10 years ago, this fraction 0.4 means that the citations happened in the first 4 years of the paper, and that's it. Or that on average, it's less than 0.4 of the total lifetime of the paper. So if you use these criteria and look at all 350,000 papers in physical review, it turns out there's only 39 papers that you could call great discoveries in physical review. So again, great discoveries are really quite rare. And it's an interesting sociological feature that of these 39 papers, before 1975, 22 out of the 25 papers that were considered great discoveries were in high-energy physics. Whereas since 1975, the remaining 14 that make up the total of 39 are all in condensed matter physics. There's been a sea change in the publication patterns inside of physical review. Whether it's that physics research is changing or whether high-energy physicists don't publish anymore in physical review, it's not quite clear. But nevertheless, there is a big change in the nature of the data. But now let's look at the citation history of a typical discovery paper. So what W stands for here is Steve Weinberg. And for those of you who don't know who Steve Weinberg is, he won a Nobel Prize in 1979 for the second unified field theory. The first unified field theory was by James Clerk Maxwell, who unified electricity and magnetism in the 1870s. And that was the first unified field theory. And one of the holy grails of physics is trying to unify all forces. And so Steve Weinberg made this next major step in unifying the so-called electromagnetic forces with the weak forces. So he wrote his great paper in 1967, and you see that he was barely cited. And then here he is in 1972. He's now hot stuff because he's getting fairly well cited. And so he was, in fact, I took the pleasure of being in his weak interactions class, where he described his theory in 1972 and as a graduate student at MIT. And he was very proud of himself because he did something great. And so 1973 comes along and he's then hired away by Harvard. In 1979 he's won the Nobel Prize, and then he's going off to the University of Texas. And what you see in the citation pattern is that he did something great. People, after a short time delay, discover he's done something great. He's very well cited. He's now at the top of the world. But eventually, the discovery, is passé at some point. And so this pattern of sudden rise and then a peak and then a slow decay is a very natural pattern that you might expect for a great discovery. When it's hot, and then it gradually gets forgotten. And 50 years down the road, no one will remember. Well, some people remember who Weinberg is, but he won't be cited anymore because his results will be inside of textbooks. The second example I want to show you is what might be called a one-hit wonder. And this actually is another colorful history. So in fact, this citation pattern is actually 2 papers on top of each other. So it's 2 different publications. But because they're cited almost together, they have exactly the same number of citations. And it's called J psi. And why is it called J psi? So in 1974, there was a great discovery at Brookhaven National Lab by the Sam Ting's group. They found a new elementary particle called the J particle. And about 6 hours later, Bert and Richter's group in Slack, they discovered a great particle themselves, and they called it the psi particle. And the two groups, and for those of you who are physicists, you know that these are two really tough-minded bastards. And so they could never agree on anything. And so they couldn't even agree on what's the name of the particles. Like if you had the hydrogen atom and you had on the west coast they called it, west hydrogen, and the east coast they called it east hydrogen, and they could never agree. And so there'd always be a new atom called the west hydrogen / east hydrogen. So here we have the J psi particle. And in 1974, the paper was published. In 1975, it was cited 160 times, and then just disappeared. And the reason it just disappeared is because they found an elementary particle that was kind of expected, but kind of not expected. But once it was found, then it's like, in hindsight, everyone said, well, of course we expected it. There's no reason to cite this work anymore because it's like it was expected. So here's an example of a one-hit wonder. Here's a third example I want to present to you, and the terminology G4 here is what's called the Gang of Four. Four great physicists came together to develop something called the scaling theory of localization. And maybe that's some buzzwords that don't mean much to the non-physicists in the audience. But the main point here is that they developed a new way of looking at disorder and how to describe dirty systems, and how transport occurs in dirty systems. And the thing about this paper, which is amazing, is that it's got legs for a long period of time. It's not like a one-hit wonder that's cited 160 times and forgotten, but it's been well cited essentially every year since publication. So this is also something quite remarkable because, as we saw early on, papers typically live about 6 years before they don't get cited anymore. And this paper, since 1980, has been cited essentially at a constant rate for the past 29 years now. So it's really remarkable how this works. In the framework of showing you gossipy type information, let me show you another type of phenomenon that is known as, in the bibliometric literature, as sleeping beauty. So in fact, there is a field called bibliometrics that studies citations in a quantitative way, not the way physicists do it. And so there is this phenomenon that is so well known that they give it the name sleeping beauty from fairy tales, which is that, there's the story of like the sleeping beauty who's like, there's some spell cast on her and she has to wait for this Prince Charming to come along and kiss her and wake her up, and everyone lives happily ever after. So I wanted to look for sleeping beauties in the physical review citation data. Don't ask me why I thought of doing this, but it's just one of those things like, you're in the shower thinking, oh, maybe there's something like that exists in data. So what do I wanted to find for sleeping beauties was, first of all, well-cited papers. So papers with at least 300 citations. But also papers in which the citation age is late in the lifetime. So citations happen more than 3/4 of the lifetime of a paper. So if a paper is published 40 years ago, the citation should happen only in the last 10 years. And if you use these criteria out of all 350,000 papers in physical review, only 8 fit that criteria. And what was amazing about this is there's only 8, I can look all of them up. 5 of them were on one subject. And in fact, of those 5, 2 of them were back-to-back in the same issue of Physical Review. And the third one was also on the same issue, but just like 100 pages away. And they're all on one subject, which is underlying the phenomenon of colossal magnetoresistance. Now, I barely know what colossal magnetoresistance is, but it doesn't really matter because the point is that this phenomenon was not accessible by experimental tools at the time these papers were written. These 5 papers, which are on the subject of colossal magnetoresistance, Zener was published in 1951. These 2 papers were published in 1955. These 2 papers were published in 1960. And so out here, from the birth of the paper all the way up, from the birth of these papers all the way up to around 1993, these papers are not cited at all. So they're the sleeping beauties, just sleeping there, nothing's ever happening. This paper got cited a couple of times over here. But these papers are essentially forgotten. And then there was a great experimental advance in the early 90s that allowed them, experimentalists, to make the materials that actually show the phenomenon of colossal magnetoresistance. And all of a sudden, these papers became incredibly famous. And so you see this incredible spike. The sleeping beauty has been kissed and has been woken up. And in fact, just for my own amusement, I actually, for this data, added the last 6 years, since 2003, And you see that it's not like falling off to zero, but it's still falling off pretty rapidly. So here's an example of sleeping beauties. Now, the last topic that I want to present to you is to use the Google PageRank algorithm to understand citations. So first of all, for non-physicists in the audience, please note there is an equation on this slide that is meant to be nothing more than just to show that an equation exists. I'm not going to have anything more to say about this. But I want to say a little bit about Google PageRank, because you remember that in our earlier showing of the list of richest people in the country, 27 and 28 were Page and Brin. And these guys are worth like, I don't know, $18 billion each. And basically, this company, this $18 billion each of them, essentially comes out of this little dwarfy equation. And for the physicists in the audience, this is nothing more than essentially a random walk-like propagation. And for the non-physicists in the audience, I'm going to present to you a cartoon that shows what this equation means. And you'll see that it's unbelievably simple. And it's amazing how sometimes the simplest possible ideas can be the source of a new company that we all use in everyday life. And so let me ask the question first before I go on any further. Who today has not used Google? One. Two and a half. So Google is certainly very popular. It's taken over everything that we do in terms of our searching. And I think it's actually a revolutionary aspect of our current day life is that you can have access to all information at all times, and certainly the Google algorithm is something that allows us to do it. If you go to the original paper by Brin and Page in 1999, it's a very simple paper. Anyone can understand it who has some training in statistical physics, and they outline their algorithm for developing the Google PageRank algorithm. So let me tell you what it's all about. There's a fundamental quantity in the Google PageRank algorithm called the PageRank. So for the way that the PageRank algorithm works is that you take the World Wide Web, and it's a bunch of websites, and they're all linked together by hyperlinks. And so each node you index by this little letter I. So the ith node of the network has a number associated with the PageRank. It's just a number. And they then found this number for every single node in the network. And so when you type into Google, like search for, statistical physics, what it does is it goes through its index of all these page ranks which are listed and says, okay, whatever matches statistical physics, I will then put it. Number one is the site with the highest page rank in statistical physics. Number two is the site with the second highest page rank. So once I have the page rank for each site, then Google works almost automatically. So I want to now show you how Google PageRank works. And so for the physicists in the audience, here's how it works. But for the non-physicists in the audience, here's how it works. And so what I'm going to use as my little experimental system to demonstrate the Google PageRank algorithm is the actual citation network of physical review itself. So just to set up the problem here, because physical review is such a large citation set, I'm only looking at papers published in a 10-year period between 1967 and 1976. And I'm only going to look at the top 1% of all papers that are cited in that 10-year span. And so I forget how many nodes are on this picture, but it's of the order of like several thousand. And so each one of these little blobs here is a paper. And each one of these lines here is a reference from a paper in the field of high energy collisions. There is a reference to something, believe it or not, to this weird molecule called TTF-TCNQ, which was really a hot field of research 40 or 50 years ago. Anyways, so here is a map of a restricted part of the universe, namely the physical review citation network over this 10-year period. And so here's how the Google PageRank algorithm works. You start with a web server, and this might date me. Does anybody recognize who this is?
The Silver Surfer?
Silver Surfer. So when I was 15 years old, which is quite some time ago, I really liked the Silver Surfer comic. So this is a very muscular, silver-covered guy who surfs a silver surfboard all over the universe. This is going to be my web surfer. And so the way the Brin and Page algorithm works is that you actually cover the entire network with web servers. And so let's just look at one web surfer. And all he's going to do is he's going to surf the web following the links. So here he goes, he's surfing between scattering theory and another paper in scattering theory, goes to weak interactions, and then he says, boring. And because he's bored, then this web surfer just starts somewhere else. So maybe he goes to metal physics and then alloys, and he's, now in solid state physics, liquid helium. That's really boring. And so then he just starts somewhere else. And so this is the dynamics of how the Google PageRank algorithm works. You just put a web surfer on the web. He just randomly goes between sites on the web, following, respecting the lines. Every once in a while, he gets bored and just goes anywhere else on the web. And you start with this gas of web servers all over the web, and you just ask, as you do this process and let it go for a long time, how many web servers are on each side of the network? That is the page rank. And once you have the page rank of each site, then you can rank each of these sites by the relative importance by the PageRank algorithm. And so, if you thought about this 20 years ago, you too could have made Google and been Richard Pickens.
You get bored randomly?
Yeah,
so
so in the original grid and page algorithm, I keep screwing up the names, grid and page algorithm, what they did is they said, well, if you're looking for something on the web, if you go 6 clicks and you found it, fine. But if you go 6 clicks and you haven't found it, you're bored, because in the new generation, you don't have powers of concentration beyond 6 clicks, and so then you just go anywhere. So that's basically what their algorithm was. 6 clicks, and then you just go somewhere else. So I think that's what I made on this page.
So who are the web surfers?
Who are the web surfers?
And then do they track people's surfing patterns?
No, they don't track people surfing patterns. So the Google people at Google have robots that are just trolling over the web all the time, indexing the web. So they launch surfers themselves. They launch all these Silver Surfers, these software programs that can then just hop between different websites. And then they just count how many times we come to different sites in the web. And so we do this process, et cetera, and just count the steady state number of web surfers at every single site of the network. We then have the page rank for each site, and then we can say, well, how important are different papers? So in this particular example, we're not looking at the World Wide Web, we're looking at individual papers, and we can ask, how important does Google say are particular papers? And the thing which is interesting here is, if you again look at this network, you'll see that there are some blogs that are big and some blogs which are small. A big blog means a paper with more citations, and a little blog means a paper with relatively few citations. And so the interesting question to ask here is, how does Google rate popularity compared to the total number of citations? And so, this is the answer from the previous slides. The page rank, which is equal to the number of surfers on the site. Yeah.
If you already have the network, and that's it, if you understand the topology network, you don't need to surf it. You just look at the network and see. And PageRank algorithm just some function of the connectivity or number of links pointing.
Well, okay, so the thing is that if it was just purely random walk, then you wouldn't have to do any simulation. You could actually analytically solve and compute the number of web servers you'd expect at every site in the network. But in this network, because first of all it's directed, there's arrows, you can only cite back in the past, you can't cite in the future. That directionality means that analytical theories of how you count the number of web servers no longer work. So you're forced to do something numerical to find this number. So if one could do this analytically, then you could put Google out of business because you could do it for much less effort. So the upshot was page rank for each site with the number of servers on the site. And the last thing that I want to show here on the story is that let's now look at the correlation between the page rank and the number of citations. And so I'm plotting on the x-axis the number of citations of papers, the y-axis is page rank. And the one thing to come away from this is that the data is nicely correlated so that if you have a lot of citations, you typically have a high page rank. But there's another little piece of irregularity in this data because you'll see that there are some papers on the upper part above this dashed line. And so these are papers that have relatively high page rank for a given number of citations. If I imagine looking at papers with 400 citations right here, there's a paper that's got really high page rank. There's some papers down here which have a page rank which is a factor 50 smaller. And so there is a class of papers up here above the dotted line, which might be called, in fact, I gave a colloquium here about a year ago, where for a physics audience, we could identify each of these papers, and physicists in the audience would appreciate, oh yes, that's why a good reason why this paper is important. And what's also interesting is that there are papers down here which have relatively few citations, barely 100 citations, but were universally recognized by this Google PageRank algorithm for being fundamental papers of physics. So the thing about this Google PageRank is that it provided a way of finding hidden gems in the literature without looking at the number of citations. On the other side, the papers that are down here below the dotted line, well, again, for a physics audience, it's almost impolite to say, like, what are the papers that kind of have a lousy PageRank compared to the average? And it turns out that a lot of these papers are in the field of Higgs TC superconductivity. Anyway, so this might be the chaff, and this is really the elite. So I've come pretty close to the end of my talk. I hope I've given you a sense that anybody in this audience can be a popularity theorist. You just surf the web now, and you can find all these great lists, and if you have some cool idea like, what does it mean if so-and-so, or is, what is it, why is something the way it is, you can find it on the web. And we have very nice data in the fields of sociology, finance, psychology, and linguistics in particular, where one has very nice data that one can look at as quantitative patterns. I hope I've given you a sense that some tools from statistical physics can help you understand popularity data. And in the context of citations in particular, we've learned a little bit about this PageRank algorithm that can uncover hidden scientific gems in literature. Now, there's still an interesting open question, which is what really determines popularity? Why is it that, to be kind of make fun of myself here, I was told that when there's talks here in like quantum mechanics or teleportation or ethereal premise like this room would be packed. Why is it that this talk wasn't quite as popular as all of those talks? What really determines popularity? And in fact, this is kind of an open question, but let me give you one more last little piece of information about this notion of what might determine popularity. So here's the results of two recent studies that were trying to quantify fame. And so this work by Maxim Simkin, who is a very free thinker, he always has interesting ideas. And so what he did is he looked at the list of all World War I aces. We just go to the history books, you look at all World War I aces, and then you just plug them into Google and say, how many hits did I get? And so, I guess this is Baron von Richthofen. I guess, as I'm looking at this data, I realize that he's not looking at Canadians, because there's a Canadian that has more kills than Baron von Richthofen. Nevertheless, I'm saying this because I'm Canadian. So, but the point is that if you look at the fame measured as the number of Google hits as a function of achievement, which is the number of kills, you see that there's a correlation, that the more famous you are, the more achievement you have. And if you try and fit the data to something quantitative, well, you see that on the y-axis, I'm going from 1 to 10, and then the same distance 10 to 100, so it's a logarithmic scale this way, and a linear scale this way. And this straight line here is a fit to the data, which is basically that the fame grows exponentially with success. So if you kill 5 planes, you'll have a certain fame. If you kill 10 planes, you'll have, So if you kill 5 planes, you'll have a certain success. If you have 5 times more kills, you'll have e to the 5 times more success, which is a huge number. And so one sees here that the most famous guy had about 5,000 hits, but once you get down to like just a few less planes, it was only 1,000 hits. And if you're down here, it's like you're barely heard of. So here you see the fame of World War I aces seem to fit this notion that fame grows exponentially with your success. But one can do a similar thing with physicists. And so this is a study by Vadro and Ben Abraham, and Ben Abraham is a lecturer next week at the same school. So they did the same thing as what Simkin did a little bit before him. So maybe it's not the same. Maybe they were first and Simkin was second. But they looked at fame of all physicists, where again they just took a list of about 300 physicists that they knew, plugged it into the Google PageRank algorithm, and just counted the number of hits. And so here's a plot of their data. And never mind whether that is shown on a double logarithmic scale, but the point is that there is a correlation that the more, the more fame that you have, and here achievement is counted as the number of papers that you've written. And this data, the straight line that goes through the data with a reasonable amount of correlation, is that fame is roughly proportional to success. So us physicists have a problem compared to World War I aces, because I can be 10 times more successful than somebody else, but I have only 10 times as much fame, whereas an ace can have 10 times as much success, and it'd be 2 to the 10 times, 1,000 times more famous. So what really determines popularity, and here is one very small partial answer, which is that if you transcend across fields, then you have a chance of really achieving real fame. So us physicists, we live in our own little geeky world where we don't really reach out to the rest of the world as well as we should. Whereas, say, Werner von Richthofen, in addition to being a very flamboyant guy, he was covered in the newspapers, and he died a very, public death and all that. And then, there's a rock band that wrote a song about him, and then the Snoopy cartoon had a lot of the story was about Werner von Richthofen. So he transcended fields from World War I military to rock to cartoons. And so this notion of transcending fields, I think, is a very important element in which one develops true popularity. So anyways, I've come to the end of my story. Last thing I want to tell you is thank you very much for coming, and I'm happy to take questions. Yes, please.
I guess I worry a little bit about your Google data, because when Google is small, its observations don't perturb the system. But when Google gets large, its observations do perturb the system.
Absolutely.
And so, at the end, whatever is, it doesn't matter what the PageRank algorithm is, because whatever Google puts up there is what everybody's going to see.
Well, so the question was once Google is so large that maybe it biases the data altogether and it doesn't mean anything. I mean, one thing I'd say in answer to it is that Google is very aware that they actually are this big monster that perturbs the web. And they have all kinds of algorithms in place to try and avoid people gaming the system. Because, in fact, a lot of people try and game the system. If I want to become more famous, I want to have some of the types of words Sid and BU that are going to show up very high up in a Google PageRank list. And so there's ways that you can say, like I can say to you, okay, I want to become more famous, you'd like to become more famous, let's have mutual websites where we refer to each other and have these mutual admiration societies. There's all kinds of scams that are out there where people try to scam the system and build up your Google PageRank. And Google itself is actually, by its robots, is looking for those things, and then they essentially blacklist you for doing it.
I understand that, but that's not exactly what I was asking. What I was asking was the act of searching. Not everybody is completely honest.
Right. Okay.
But the act of searching with any PageRank algorithm produces a number one that all of us look at and see as number one, and therefore it becomes number one.
Right. Okay. But on the other hand, I think this is also coming back to this point of the rich get richer. Before the web ever existed, if you just look at the citation patterns of physical review, the rich got richer. So you're correct that when Google puts somebody, Michael Jackson's funeral, number one on hit parade, and everyone looks at it, so it becomes even more popular. It's a self-fulfilling prophecy, but it's essentially a realization of the rich get richer.
Two questions. The first one is about the zero citation papers.
I don't know who they are. I don't know those types.
Just as an index of how selfish physicists are, how many of those are, if you had a chance to look at how many of those are at the end of the loop, like the last paper someone wrote?
Oh, I've not looked at that. So, I think this is a study. I'm interested in popularity. I'm not interested in unpopularity. So I'm sorry. I have nothing more to say about it. Just inside the numbers.
And just as a thing to check the transcending fields, does this apply to physics? Like, are there people like Pierre Gents, for example, who transcended a couple of fields? He was working both in superconductivity and polymers. So if you transcend fields... I mean transcending fields in a much broader sense. Pierre Gents is a truly amazing physicist.
who made contributions in superconductivity and liquid crystals and polymer physics. He was a real classically trained physicist who could do like all the hard field theory calculations, and later in his life, he didn't do any of those kinds of things, and he just always waved his hand and got the right answer. But I don't mean transcending fields like that. I mean transcending fields like Einstein is a very good example, where he became part of the popular culture. Or, Carl Sagan, who, was a well-known astronomer who became part of the popular culture and like the host of Nova programs and things like that. That's what I mean by transcendent fields. Like the same way here that Bernhard Richthofen, he never dreamed in his life that he'd be like part of a Snoopy cartoon for 5 years and all the theme of Snoopy cartoons.
In France, the scientific part.
Yes, in France. Yes. Okay. Yes, of course.
I'm not confused by what you said about capital N over little n, because if you say the increase is proportional to the thing itself, you were at exponential growth, wouldn't you?
No, the thing is that, you'll have to come to my talk on Friday, where I'll show you how a growth rate is proportional to the current number of citations gives rise to this scale-free network, not exponential growth that gives rise to power law growth. So, I'll show you on Friday, and you'll believe me. I know you'll believe me. Yeah.
So, referring back to that same statistic, that the number of new citations is proportional to the number of existing citations. You said this was a result of complex individual. But I thought this had a very simple explanation.
Okay.
And not to say I do this, but suppose I read your paper, and it's interesting, and I want to do some further development of it,
right.
And I write my paper. Well, I can't just cite your paper. I have to sound like I know what I'm doing.
Right.
So I look at your paper, and I just copy all your ideas. And that's how it goes.
Okay, well, actually, you said something very profound, because this notion of looking at an average person, say my paper is an average paper, and then you look inside and cite some of those. On average, the citations that are inside of my paper are more popular than the paper that I've written. And in fact, there's a very nice experiment you can do, is I can pick a random person in this room and say, how many friends do you have? Say you have 7 friends. But then, if you go to one of your friends, your friends on average will have more friends than you yourself. And it's a strange feature that is part of, I think, might be a generic explanation for why there is this linear growth. So but nevertheless, the point is that this individual behavior somehow translates by the copying mechanism or some kind of redirection mechanism to something which then becomes simple and emergent.
Can I just follow up on this? So you're saying this does not explain it, or at least just copying citations?
I personally think that copying citations does play a huge role. That might be a lot of the explanation, but there's not I have not looked at the data in a way that could decisively say that this is the mechanism as opposed to some other mechanism.
Just to continue commenting on the one, I remember many years ago now that someone told me something quite amusing about the same story, which is that a paper has 4 different levels of space. The first one is 0, and you're not cited at all, right. Red and what have you. And the next one is that you're cited in red. The third one is cited but not read.
Okay.
And the fourth one is you're not cited at all, like Newton and Einstein. So you might find it interesting. I don't know how you can find out whether a paper is cited and not read.
Well, this is probably something which will be available in the next couple of decades, where one has contextual information associated with citations. Because another thing with this whole story of citations is that we don't know why a paper is cited. I can be cited because I'm wrong all the time, and people like to cite me because Redner's wrong all the time. You can be cited because your thesis advisor said you should cite this person, or that you didn't cite somebody and the person got angry at you and then said you better cite my paper or else I'm going to blackball you. There's lots of reasons why you can be cited, not just quality.
I have a comment about gaming Google. It's actually actually a big industry. It's called search engine optimization. From what I understand, it's very well paid.
Okay. Good way to become popular. We will pay.
Google works very hard against those people. And they pay people a lot of money to beat those guys.
Yes.
I have a question on the last two you showed with ACEs and physics published papers. Is there some sort of like self-selection in those where if you publish your first paper and it does not have a lot of fame, the chances are you're not going to try and publish another one. But if your first one gets you a lot of fame, then you'll publish more.
Yeah, I mean, but I think that the same self-selection happens both with World War I aces and with physicists. So, like, the typical trajectory of a physicist is that you start publishing papers, and if they're crummy, you're not going to get tenure, and then your career's over within 5 years. And similarly, if you're not a very good pilot, you're going to be shot to go up. Yeah.
Is it accurate then to say, the number of papers published? It's not accurate to say I can go write a lot of papers and therefore I'll become a good physicist.
Right. I mean, it's the other way around. Your first bit would be at least above a certain threshold of ability before you can start writing papers and stuff in the water. The same way that you're not going to become a World War I pilot. First, you pass the physical fitness test, you have good vision, you show good coordination before they're even going to let you step inside the plane. Yes.
Out of curiosity, you mentioned Learn on Vertical, right? Who were the two physicists on the right of your physics?
I don't know. See, so that's part of the thing about statistical physics is sometimes we don't care about the individuals, we only care about the statistical information. So, I mean, if you look at Ben Abraham's paper, you'll find the names of these physicists. Actually, he's here next week. Ask him. So,
when the Weinberg paper started to lose popularity, was that at all correlated with the time that the strong force got coupled in with all?
No, I think it's more that it was clear that it was the theory. And so once it was the theory, people stopped working in the field because Weinberg solved it. Weinberg's the law of Blaschall. They solved it. And so this is no longer an open problem. So there's a few hangers on it and kind of cleaned up a little bit of the loose ends, but it's no longer current. So I don't think it had anything to do with any other field. It's just that they solved it.
You mentioned the class 1 idea resistance. Part of the issue there was that it became technologically very important as part of argument.
Right. But again, the point was that they couldn't make those like thin film semiconductors until like 1992, and then Volkio exploded.
Any other questions? If not, thanks Sid again for